Good afternoon, everyone, and it's a pleasure. A little bit nervous to present to you what Jafar and I did in Germany, density functional theory, and our project to apply what we learned is called optical properties of ruby crystal. So this presentation will be two parts. First, I'll introduce to you a bit about density functional theory and its different versions that you have seen from Jafar previously. And the second part, we will discuss on the optical properties of ruby crystal. So on the first part, if you want to study many particles, so we just have your regular Hamiltonian, and we sum over all the particles. So we have the kinetic energy term, the external field term, and we have the interaction term. And to make some short notations, we have the vector x, where we will define on the 3D vector, R vector.
Do you know that you have a pointer? Or you do have yours?
Yeah.
Is it?
Yeah.
Well,
Yeah.
it's remote adjusted. Using telephone to do remote control, right?
Yeah, I've
Yeah,
seen
yeah.
it. Sometimes I had the feeling you couldn't point.
Well, I can't control.
That's
Yeah.
why I was telling you
Oh,
you
okay.
have a pointer.
Okay, yeah, thanks. And yeah, I'll just move the mouse away. Okay, so we have the vector x here, and it's defined on we combine the spin of the particle and the three-dimension space R. And next we have the integral d4x, so we call it the integral on the 3 dimensions, and we sum over its spins. And finally, the delta function x minus x prime is the product of the spin prime and r minus r prime. Then now, if you want to look at the energy, we do a summation. We do an integration over n particles. So since we have the d4 here, we have 2 to the n integration. So that's a lot of work to do. So to make things a little bit easy, we have the 1 particle density, rho 1, and we have the 2 particle density, n2. So the 1 particle density is simply just n, and we integrate over n minus 1 particles. For the 2 particle density, we have the integration over n minus 2 particles, and we sum over particle 1 and particle 2 spins. Because the reason we do that is because we have r here, and this one is defined with x. So knowing this, and we put into our energy, so we have a slightly longer term. So in this case, we make use of the 1 particle density and the 2 particle density here. So the 1 particle density is acted by the external field and the kinetic energy term. The interaction term is acting on the 2 particle density. So to make it more of a density functional theory, so this is plucked from Professor Peter's textbook. So we have this is a way on how we see a functional looks like. So we have the kinetic energy here, and it's a functional of 1 particle density. And over here we have F, which is called the occupation number for every particle. It takes values between 0 and 1. And we have a bunch of Lagrange multipliers here and here. So instead of external field, now we have the effective field. And if we plug the kinetic energy terms, the potential energy and the interaction terms, so we'll have something even longer. So this is more like a functional. And if you notice here, we have something called the exchange correlation energy, which we will see later on. So you have seen what Jafar has given, LDA, GGA, and these things, if you recall the ladder that he shows you. So, but before that, minimizing this whole thing, so I believe it requires a lot of work, but in the end you get something called the Clon-Shams equation, where it's defined on the effective potential energy.
So Alexander,
Yeah.
can you go back to the previous transparency?
This one.
So here you have been claiming that this should be a function of the density, but honestly I don't see that. It's just
We have it right here. Yeah.
But you also have the wave functions. The wave function should disappear if it was a function of the density.
The only way I can explain is if you have this thing acting on the density, so I think that's where it disappears.
But you're taking a minimum on
Yeah.
what?
Yeah.
What I read is something like
Okay. We take the minimum of the energy from the different fn's and the wave function psi. So this should be in a way that it minimizes the kinetic energy. So we have to play around fn and psi.
Oh, well, this is flawed and can't actually do the minimum. So this just proof existence.
that's a difficult issue probably, but at least I understand why it is not depending on it.
Well, as far as I can tell, the end is here, so that's how I see it.
And was sure.
Yeah.
The question was why not psi?
Why not psi?
But it has been minimized on psi. How?
Well,
Let's see.
I'm up to speed, thank you.
It's okay.
Well, I believe so. So you have here, you already integrate on the psi.
It's okay. You have taken a minimum.
Yeah. Okay. Yeah. So we have the Clon-Shams equation here, and then next, so to address the energy correlation, the correlation energy. So one way to look at it is the local density approximation. So in real life, solid states they have an inhomogeneous electron density. So LDA assumes basically a uniform density here, and after a long derivation, so we have the final results here, and finally we consider the electron density as a function of R. And next we have the generalized gradient approximations. So this time it takes the formula takes the electron density and also its square gradient. And superseding these two, we have the projector augmented wave. So this is the theory that we're using in our project. So we take the wave function psi, we define it as the operator T that acts on some pseudo wave function. So the pseudo wave function is defined from a pseudo potential, and Jafar has pointed out pseudo potentials earlier. So the pseudo potential, we say, is a sum over many partial waves, and what we want to do is we want to find an explicit form of T. So it's given like this, but we want to know even more, namely what does SR look like. So if you just take a partial wave, a pseudo partial wave, and we have T to act on it. So, and then we rearrange the term, we get SR. And if we plug this back into here and this back into here, so we finally have an explicit form of the transformation operator. So now that we know, so now that we've seen how the transformation operator looks like, and suppose we want to look for an observable, for an observable that incorporates the transformation operator. Well, it turns out that if you look at the average of an observable, it is simply its operator sandwiched between the brackets, and then we take what we know about t and this equation over here. So we define it. So we define it instead of the full wave function. We define it on the pseudo wave function, and let's call a tilde the operator that acts on a pseudo wave function t dagger a t. So what comes next is a semi straightforward mathematical step. You plug everything you know in, and you arrive to this expression right here, which is a lovely expression because our our a tilde operator looks pretty much like the transformation operator here. So yeah, that's the first part of the presentation, density functional theory, and off to the second part. So we're applying mainly the projector augmented wave method onto studying optical transitions of ruby crystal.
So, Alexander,
Yeah.
maybe can we ask a few questions on the first part now before you move on to the second?
Sure.
Okay. So I want to ask one thing. I could have asked Jafar also, but let me ask you. Can you comment on the meaning of the physical meaning of the Bourne-Champ wave functions?
Well, as far as this one right here. So as far as I can tell, the actual Hamiltonian uses the external field, but the Kohn-Sham equations use the effective field. That's how I understand.
In other words, the question is the epsilon n that are here, the equation where what are you going to do with them, and what can you comment on the epsilon n that equation, what they mean?
Sorry, you mean comment on this one?
This energy here, what is it?
Well, I just simply see it as a Kohn-Sham energy, but
But physically?
yeah. Well, I don't think it will represent the exact energy of the system, but I can't comment beyond that.
Well, so let me pose a different question, but it's a related one. So what is the Hornberg-Kohn theorem actually telling you?
Sorry?
What is the Hornberg-Kohn theorem telling you?
Room?
The Hornberg-Kohn theorem is basically what are motivated here.
No,
Can you say the theorem that you...
I don't know the theorem, I'm sorry.
But at the heart of the density function theory, I mean, if you go to the previous transparency,
This one?
yeah, what we said basically the kinetic energy is a function of the density.
Yeah.
But that is relative for what? I mean, for what? Under what conditions do you valid?
Sorry? What?
Why is it not always true, or in which condition
What
is
are the
it
limits?
true, or...
What are the assumptions that you need to prove it? Yeah? I mean,
This is not completely general, so what are the limits or conditions, or...
I guess I can't tell the limits. Well, apart from the fact that we have an effective field and it's different from our external field and yeah.
So what I'm getting at is, you know, a many particle system has lots of states.
Yeah.
So is that valid for an arbitrary state, you know, or is it only valid for? I mean, you have a minimization principle that might
Yeah.
be a minimization. And
Well, from what I can tell you, it is for an. I think you can put it on an arbitrary state, because I don't recall reading any limitations it mentioned.
so my understanding is it's actually the fundamental here is only basically valid for the bound state. You get a pseudo energy from the Bourne
Yeah.
equation. Then what do you do in the end if you do excited state computations?
Well, I've never seen it done on excited state computations or only ground states.
I
Yeah.
mean, okay, I will get back to you, but if ground state.
Yeah.
That makes physical sense from the computation, yeah? But probably going to do more. So in fact, you are using the Grunscham equations in a regime where, or the Grunscham energies where they're not supposed to make sense. So you're going beyond the original regime of justification when you apply the things. So if you compute a band structure, whatever, this is the outside beyond your assumption that the equation is applied.
Okay.
Everybody does it, yeah. But okay.
Okay.
I'm fine with questions. Shall we let me continue or do you have
In
questions?
fact, in the previous slide, you not this one.
You should put numbers and
You speak about the density of two particles.
Yeah. This one.
And after there is not. Why don't?
Oh, density of three particles.
What do you do?
why this
Well,
N2 is not in
What
the
this
business?
and why are you speaking about this N2 and how it disappeared?
And to we no just to make things simpler, so we introduce the N2 so that it can be put into the interaction term.
And
Yeah.
after there is no just to present.
Yeah, just to present this. Yeah.
But it should actually disappear in some way.
The effective potential.
So it should boil down to a single particle density again in the ground state, yeah. So for kinetic energy we've shown that, but for that must also disappear somehow.
All
Yep.
those formula you have taken them from the book you indicated before.
Yes, from Professor Peter's book. Yeah. Well, there are other references also that are similar. There is one book that has a factor half here. But it does not include this spin. So I think that if you include this spin, then the half disappear. But essentially the same thing, I believe.
Yeah, it's not that definition.
Yeah. So I continue to the second part.
Sure.
Okay. So now we apply we apply the projector augmented wave method into our project and to study ruby crystals. So to set up a ruby crystal, you need something called a corundum crystal, which consists of pure aluminum oxide. And the pure aluminum oxide is a hexagonal close packing. So you have oxygens packed up in one layer, and the aluminum atoms are on top of the gaps of the oxygens. And to produce ruby crystals, we introduce chromium ion impurities. So it would help to know how their electronic structure looks like. So this is the atom. So what we're introducing is the chromium ions. So it's important to take note. We have 3 valence electrons in the 3D orbital, which would be important later on in our optical transition case. And if you want to make other things besides ruby, for example sapphire and maybe emerald, you introduce iron, titanium, and vanadium.
Instead of the chrome.
Instead of chromium, yes. So there are different, well, sorry for the missing things here, but so this is pink ruby, red ruby, dark red ruby. So these are different concentrations of chromium ions in your crystal. Lightly doped less than 0.1%, medium doped between 0.1 to 0.5, and anything higher is heavily doped. So in the literature, Jafar and I found that if we're studying ruby crystals, lightly doped ruby crystals are very well known because in the crystals the chromium ions are far apart from each other that they don't pose complicated interactions. And if we look at medium and heavily doped, they are close enough to cause some sort of complicated interactions. So in our project, we have 3.3% ruby. So in our structure we have 30 atoms. One of them will be chromium, so 3.3%. And we do not consider the effects of concentration of ruby on our optical transition, concentrations of chromium.
So Alexander,
Ruby
Yeah.
in chromium?
Oh, if the chromium is inside the aluminum oxide, it is the impurity, then it becomes a ruby crystal.
So you think that you say that there is 333%
Yeah.
of impurity
Yeah.
in your chromium.
Yeah. It's no in the ruby.
but if you go
Yeah.
back, so Alexander, if you go back to the atomic composition with aluminium 2O3, so if you now replace 1 out of 30 aluminium with a chromium, which gives you that percentage, that needs probably more than 30 atoms to do that, because you also have the oxygens.
It's a percentage of
Of
what?
aluminium.
Of aluminum
Oh.
or-
No. So you have 30 atoms. So you have of the 30 atoms, you have 2 parts are aluminium and three of them are oxygen. So we just take one aluminium out and replace it with a chromium.
So
Yeah.
it's a percentage of all the atoms.
Yeah.
Okay.
Percentage of the atom.
Not percentage of aluminium.
It says right here. Yeah. And also in the same literature, it says that the total spin is a good quantum number to study our optical transition, and not the angular momentum, because it says it will be quenched by the other atoms in the crystal. And yeah, so if we talk about optical transitions of ruby, so we have to talk about the selection rule. So we introduce something fairly short, the transition momentum integral. So this is called the transition operator. It acts on the initial state and maps it onto the final state. So a transition is allowed if the integral does not equal to 0. So in our case, when we do the ruby crystal, we found that if delta S is plus minus 1, then the transition is allowed. In our code, when we flip a spin, we have a delta S equals to plus minus 1. So and we did find an allowed transition, which reinforces what the literature say, and that's why it's very important to look at the 3D3 valence electron.
So Alexander,
Yeah.
I'm actually a bit surprised by this optical that you say delta S is equal to plus minus 1. If you change the spin, it has to go somewhere. I mean, so where is this delta S coming from? Where's the magnetic change of magnetic moment going to?
We're not seeing the magnetic moment, but instead of the state. So we first start off with all the spins pointing up. For example, we change one spin, and then is delta S plus minus 1. Yeah, and that's what we did in our computation.
For the 3 electron of the chromium.
Yeah, from the 3D.
But it's funny because an optical transition operator should usually be spin conservative. It should not change the spin.
Conserve it.
Yeah. Fluorescence.
Pardon?
Fluorescence maybe not.
No,
At
but
least
the light is not carrying a spin away. I mean, it has to go somewhere.
Oh, your understanding is optical transitions that doesn't change the spin?
No, the light doesn't have spin, so you cannot carry a spin away by light.
So
It has
where
to
Oh,
go-
is
this is from the chromium. The delta S is from the chromium. The chromium's
So it means that
electrons.
something else has a delta S.
Yeah, somehow.
has to be absorbed elsewhere.
Who is absorbing that is the question.
Well, the typical answer is
You think that globally you get that? It's not another local
well,
stuff.
it's contradicting what you said before. One way out is that you say that actually the spin is not a constant quantity. Then no problem. But
It should be. I mean, if you take the total system,
yeah, the total system, yes, but the local system might not be
Local,
conserved
probably not.
because of the environment. That might happen, yeah.
Yeah, but this is total.
is it the total this one?
Yeah. From what we did, it is the total because when we do the simulation on 30 atoms, just one atom is a chromium, so we just study that chromium.
Well, we should have asked that Jaffa why you say that, but since you write down about all the matrix elements, I don't understand it any longer.
Yeah, no, but maybe not. It's not the total. It's one of the chromium.
Yeah, from the chromium.
Yes,
Well,
it's not
I'm
the
only.
total.
Oh, okay, sorry, fine. So yeah, this is in regards to the chromium, but you, from what I understand, you're saying that if it's optical transition, the spin must be
If you
constant.
take the whole system.
Yeah. Okay.
The photon, once it comes out, it cannot carry a spin away.
Yeah.
It's
Okay.
normally
Yes.
There is no way that you have this conservation of a degree of.
Okay, got it.
But probably it's somewhere else in the structure of it. Where?
Okay.
And in the process that Jafar showed,
He was flipping.
He flipped the spin 2 times.
Twice, yes.
So finally it's conserved.
Yes, there was a
But
plus
I
one
don't
and then a
know-
minus
yeah,
one.
but-
Okay.
And this is just for one step.
But I thought it
But
was a
it-
purely theoretical.
Well,
I thought it was in the program. I didn't
Yeah.
thought it was in reality, so I reacted differently. He told me with flip spin if you want.
Well,
Whatever you want with your spin.
Okay.
Now if we are talking about matter, I see things differently.
okay. Well, you're referring to the energy diagram. Well, I'm going to show the same thing, so we can see it later.
I'm very sorry, but
Yeah.
actually I've done things like that, and we have had a big problem because we had to argue the matrix elements were non-zero, except for that as equal plus minus 1.
So actually he was
Okay.
So
very involved in the question.
Okay. So yeah, good to know.
Physics is tough.
Yeah. So when we're doing our simulation, well, this is this is how a pure conundrum looks like. Another assumption we make besides the effects of how many impurities you put in is that we consider we consider a perfect hexagonal packing at the start of the program. In real life, in the same literature we read, we found it mentioned that the structure is not perfectly hexagonal close packing because the oxygen atoms distort the structure a little bit, but we ignore that. And yeah, so you can see the added chromiums here and there. And okay, so
The chromium you had is
so
I
this
don't understand. So you put it randomly?
This one. So this one is an enlargement of our 30 atoms. So we structure 30 atoms, and then from the Avogadro program we just expand it. So we're seeing a repeated.
Oh, there is several cells.
Yeah, it is similar. Yes. Yeah, we're just repeating it.
It's not random.
There's one problem atom in the insurance cell, right?
Sorry.
There's one problem atom.
Yes.
So what is a bit strange is that I actually do see 2 chromium atoms that are pretty close to each other.
Okay, so let's look at this one here, and here. So if I recall, this would be one cell.
Oh, but you put chromium on the 2 sides.
Where's, if you look at the left edge, there is.
Yeah, these two.
These two.
Where does that come from?
It may be a matter of projection.
In that regards, I'm not sure.
In third how high is it? Just one layer that where you have the kinetic and then the repeated layer? Is it the next layer below?
Ah, yes. Okay. So what? Yes. I think yeah. This one layer here and one layer here, and then we repeat some more up here. That's one way to explain. Yeah.
So this means in the vertical direction, there's pretty close. You see that
You mean vertical? Like that. We agree that this is
Like that.
vertical.
I mean layer direction, which is probably perpendicular to the projection.
Yeah, okay, that's what I meant. This is two frames.
Yeah.
It's not a local vertical.
Okay. So.
Alright.
So here, the density of states. So you've seen this from Jafar. So we have the total density of states here, and it's composed of three different atoms we have in our cell. So over here represents the s orbital. Here is the p orbital, and if I'm not mistaken, including this one, these are the d orbitals. And we have the occupied states from S all the way here, and unoccupied states from here all the way here. And you did ask about the Fermi energy. So if I'm not mistaken, the Fermi energy would be somewhere here. I mean, because you have occupied states all the way here. So I believe the Fermi energy would be right here.
Yeah, close to 13.5 because it's the highest occupied state. So
Yeah.
on the agreements.
So if you want to study the optical transition of ruby crystal, this is our most important graph. And yeah, it's very interesting to see that you can't see at all the occupation, the density of states on the s orbital. You can see a little bit of the p orbital. And over here we see p orbitals of the chromium, and in our simulation we put all the electrons spin down, so that's why we have a peak pointing down where all the 3 electrons reside. And when we flip the spin of the chromium atom, so we have 1 electron spin pointing down, 1 electron spin pointing down, and we have 1 electron spin pointing up. So there is a reason why we see a red and a occupied here and an unoccupied here. So Professor Peter actually gave an explanation why this happens. Long story short, what he says is that there is a bug in the programming when it wants to illustrate the graph. So by right, this peak should be colored red instead of pink.
Full red.
Full red, yes. Yeah, he mentioned something about a shift in the Fermi energy, so maybe that's why we see a partial red here.
Due to temperature? Due to when?
As Jafar mentioned, structural distortions. And okay, so here, Jafar has explained the graph, so I'll quickly explain the graph as well. When we did our simulation, we started, we composed our structure, and we found this energy to be as such. Hartree energy differs from electron volts by a factor of 27.1.
This is now the structure with the one aluminum replaced by chromium.
Yes, yeah.
Is optimized the structure or is it not optimized?
I don't know. Every simulation we did was optimized.
You
Yeah.
mean the position of the atom is optimized?
Yeah. The structure, the position, yeah. so it's excited to this energy here, and every level is worth probably half an hour to 40 minutes computer running. So we run again, we have a relaxed state, and
With the disadvantage, there's a second time I'm hearing it, so I have better understood what I haven't understood previously.
okay.
So the question is, how do you make the excitation? So I thought, since you already have the impurity atom in this lower state, how do you make this?
Okay, so we first started off with 30 atoms, and Professor Peter gave us how the structure looked like. So in our program, we write down we write down their coordinates, and then initially we simply take just one aluminum atom and replace with a chromium. Yeah, that's
This
it.
is for
And
the starting state.
yeah, the starting.
And after for the
Then how do you excite it?
Okay, the excitation, I don't quite remember, but we distort the structure.
I don't remember how.
Yeah, so Jafar mentioned about the control file. So in the control the control of the program. So in the control of the program, you specify the spins, the structural distortion, and among other things. So we did something to that coding line.
So you're going to tell us in a second that you relax it. The question is, why doesn't it go back to the original state if you relax it? How do you prevent it from being stopped?
Okay, so all right, yeah. I'm trying to recall the procedure, so bear with me. So we have a structural distortion, and then from that code we keep everything the same, but then there is a small line that we say from there we just relax, and but still the entire code would be different from the control file would be different from this ground state, if I can remember correctly.
Relax means that
The structure relax.
the
We recompute from here.
And
optimized
you optimize the
position.
Yeah. Yeah.
So you re-optimize the position.
Yeah.
Okay, so
So
the idea is that you give energy.
Yeah.
In a way.
Mm.
So it gets some structure
Yeah.
that has more energy, but it's not optimized. So now it readjusts to this
Yeah.
additional energy.
Yeah. In any case, the code, the control file, here, and here are entirely different. All of them are entirely different.
And physically, because when Java was explaining that, I was taking it as pure numerical things, in some sense. Here, for me it was not clear that these different states were taking place in nature, do they? The real crystal evaluate in this real way?
They do, because you have different types of transitions when you decrease your
It's
energy.
not just
Some of
something
it are
you're doing for the
radiative.
modernization.
Some of it are radiative here. Some of it are just
All these
non-radiative.
different states
Yeah.
are measured experimentally in some sense. Exist.
They should be, because I mean if we look at level systems. Yeah.
This distortion probably was observed experimentally.
Okay. No, I don't know why they do that. That's what
I can give you a paper that's saying that they are talking about the geometrical distortion. And probably, in fact, we have more than those levels. In fact, we have more levels. This is just a part which calls fluorescence. In fact, we have more phenomenon included. Just in this case, we are trying to reproduce. In fact, there's nothing new.
Yes.
But about the
Yeah.
energy between the first relaxation, the energy are very close.
Yes.
So
Yes,
probably
very
the
close.
position of the atom is very close, almost the same, and you go to the first minimum.
Yeah, I guess.
And you have to mention another thing. We do optimization for positions and wave functions. We do also optimization for wave functions.
At each level.
Yeah. There's two.
Yep, but you see, what is bothering me is if you take let's say a simple lattice and you just pull it one atom a bit, you let it relax, it will go back to the original place. So you have to have done something that prevents relaxation to the original place. And if you do, let's say, tilting and you change the symmetry, spontaneously it will not go back to the same symmetry. It must be something like that, yeah? Then you
more than just a simple move.
just moving at them a bit would go back to the must be more complex than that, I think. And it must be related to the component keyboard. I really am no expert, yeah. But okay. So
Okay, cool. So yeah, from here we flip a spin, and again we allow it to relax. And finally, to obey our selection rule, I hope we all agree on the selection rule. Delta S plus minus 1, so it comes back here, and we have a fluorescence. So our energy difference is 2 electron volts. We calculated and we converted to electron volts. In real life, that would be an orange ruby crystal, but ruby is supposed to be red, 1.7 or 1.8, and it has 2 different wavelengths, very close to each other. But here we do our simulation is for just one type of wavelength, and
so the number that you're getting is too big.
yeah, too big. So we suspect one weakness to our result is because we didn't let the computer run fast enough, long enough. Yeah, because we were running out of time. We wanted the result.
And so the result is good.
Alexander, I have
Yeah.
one more physics question. So once you have done this transition, you start from a relaxed situation and you end up in a non-relaxed. And it doesn't make physical sense.
Which level?
The fluorescence transition. So
Yeah, and here.
the initial state is relaxed and the final state is not relaxed. Does that make sense?
Okay, so every level we run is a simulation. That involves the computer computing our energy, and from here to here. So okay, you notice 327117 is the same thing, but there is actually a few decimal
Okay.
behind the discrepancy. So that's what our calculations found.
So it means the spin, when you flip the spin, these have almost no effect on the position of the atom.
From here to here.
Yeah. The relaxation will have no effect.
Well, I won't call it a relaxation yet, unless you go from here to here.
Ah, you are relaxed from.
Yeah.
Okay.
So Alexander, what I was trying to ask before, if you flip the spin and you emit the photon, it might be that the photon emission is a lot faster than the relaxation of the lattice, and therefore there might be an argument not to relax the lattice to complete the transition. But if you tell me anyway it doesn't matter, I'm yeah.
Well, okay. So you're disagreeing with this transition here.
Now, if there would be significant difference between the two levels, then the question would be what would be the physics question, what do you take as final state? Between which states do you take the energy difference? Yeah?
Ah, okay.
And I was trying to justify what you have done.
Okay. Got it. Yeah. Yeah. Okay.
Yeah,
I
it
see.
doesn't make a difference,
Yeah.
obviously, as you said. Okay.
Yeah. And also when we saw the numbers, I found it quite strange that this number here and here are very, very similar. They differ by very small decimal points. So yeah, that's pretty much it. This is the reference we use. What I found interesting is reference 1 comes from the American Air Force, and somehow they were studying ruby crystals. I don't know why. Yeah. Yeah, so that's it.
Thank you very much, Alexander. You're all in, but you're quite a bit in the middle. Any further questions? We'll get one first question session in the first half. In the second half, we interrupted you. Any need for further discussion?
Oh yeah, can we, if we go back to the selection rules? Yeah, so so Professor, you were saying that for optical transition, the spin must always be conserved. Just to recap.
I mean, if you emit the photon,
Yeah.
if you emit the photon that has no spin,
Mm-hmm.
but if you would emit a neutron that would have spin, and then it would be natural that the spin is changing in the transition. But I mean, you have to you have to adapt the quantum numbers of the initial and the final state. So the photon that goes away doesn't have spin away.
Yeah.
That means that the solid
Yeah.
has to have the same spin quantum number as it had before.
Okay, got it.
If spin is a good quantum number.
Okay.
You can change your, of course, the chromium. And at the same time, changing otherwise. But the most naive copy usually gives you delta is equal to 0.
But probably in this calculation, you can find that the energy involved in the change in the structure is the good order of magnitude for this photo. And then probably in real life is different. Maybe there is a spin flip of in all the system that you take into account, but it will change nothing because the spin flip will change so much the energy.
But the position that's actually computed is created for the spin flip, yeah?
The spin flip on chromium.
Yeah. There's one spin.
Maybe there is another one on the matrix.
So actually, this emission seems to go with the spin flip on the chromium state. So they seem to have different spin quantum numbers.
That is the question. Because in the process they use, they split one spin and we don't know why.
Yeah.
That's why I was not imagining it was physical. I thought it was
Yeah,
like
it's not complicated.
process of the computation.
Also, I mean, with respect to the relaxation, I mean, if the spin quantum numbers of the two states that you're targeting are different, then you have a clear reason why, even if you relax, you get different energies, yeah? Because you have a quantum number that is distinguishing the two states.
Okay.
So that is technically also very nice because you can fix the quantum number and do the difference, yeah? Between the two. But still, why should an optical transition between two different spin quantum numbers?
We should, if we want a transition, we should have what we call different parity. Parity on spin and on a transition.
Well, it might be, so Alexander was saying, I'm not sure, but let's suppose that what Alexander was saying is correct, that orbital angular momentum is quenched and spin is not. So that orbital angular momentum is not conserved, but spin is. You see the quenching, do you know what quenching of orbital angular momentum means?
So the quantum number L disappears.
Yeah.
Yeah.
But it's basically coming from the fact that the atom is sitting in a non-rotation symmetric environment, and therefore the spin gets frozen. But
Okay.
Usually the orbital angular momentum contributes to magnetism. So if you break that symmetry, then you have a way how to change the spin because of the crystal fields, and if you break that local rotational symmetry, but then it would be strange that you said that S is a good quantum number.
Yes.
So I mean that has to It's usually cross-field effect from the neighboring atoms, like in like the symmetries, and then you can allow these transitions.
Okay.
Simple.
Okay. So we are really getting into the fine details. Should we stop it here?
Yeah.
Yeah, yeah.
Okay,
So
thank you.
we thank you and we ask for a few minutes of discussion.
Okay.